All right, so welcome to chapter 10.3, where we're going to talk about transmutation. Yes, we skipped chapter 10.2. So as mentioned in 10.1, transmutation is the conversion of atoms of one element into another, meaning in the nucleus, it changes the number of protons, because the number of protons an atom has defines what element it is. And attempts at transmutation go back to the age of alchemy in the 1500s and even before. Alchemy was mainly the predecessor of chemistry, and the ultimate goal of most alchemists was to make gold out of things that were really common, like lead and mercury. While this is not considered strong science anymore and is not considered chemistry, the alchemists did do a lot of things that came before chemistry and led us to a lot of the discoveries we know today. Now, transmutations occur naturally in radioisotopes. So, in uranium-235, that is an unstable element, and it will naturally decay into a different element over time. But scientists can actually perform artificial transmutations by bombarding atomic nuclei with high-energy particles like protons, neutrons, or alpha particles. So, for example, in this picture here, this was a transmutation that Rutherford did in his lab, where he took nitrogen-14, 7 protons and 7 neutrons, and he bombarded it with alpha particles. And these alpha particles came from uranium salts. He just left the uranium salts laying out in contact with the nitrogen-14, and over time those particles interacted with the nuclei of the nitrogen atoms to produce oxygen and an extra proton. Now, all elements heavier than uranium don't occur in nature. They're transmutated from lighter elements, and they are artificially transmutated by scientists. And these are called the transuranium elements. So you can see uranium is somewhere in here, right here. This is uranium, number 92, and every element with a number higher than 92 is a transuranium element. It is an element that was created artificially in a lab by bombarding a smaller atom with a smaller nucleus with certain types of particles. Now let's do a sample problem of what this would look like. This is going to help you out on one of your homework problems. So the first sample of californium was made by bombarding a target isotope with alpha particles. In addition to californium-245, the reaction produced a neutron. What was the target isotope? So what we're trying to find here is what element did they start with in order to make californium? So what we need to do is we should set up a chart. We should set up a chart of the number of protons and the number of neutrons. And we need the before numbers and we need the after numbers, because these should match up. They're going to take different forms in terms of what kind of element they're creating, but the number of protons and the number of neutrons will not change over time. So, in the before, we have an unknown element. So we don't know how many protons it has and we don't know how many neutrons it has. But we do know that we have alpha particles. And if you remember correctly, an alpha particle is just like a helium atom that has an atomic number of 2 and a mass number of 4. Now, if it has an atomic number of 2, that means it has 2 protons. And if it has a mass number of 4, that means it has the 4 protons and neutrons together. So if it has 4 protons and neutrons, and we know it has 2 protons, it must have 2 neutrons. I just took 4 minus 2, and I got 2. Now, in the after scenario, we have californium-245 and a neutron. So this little neutron is just a standalone all by himself over here. But californium-245 has a certain number of protons and a certain number of neutrons, which we can find using our periodic table. So if you look at the periodic table, californium is number 98, which means it has 98 protons. And in order to find the number of neutrons, we have to take 245 and minus 98. And if we go to my handy dandy calculator here, because I can't do math in my head, 245 minus 98 is 147. So we end up having 147 neutrons from californium-245. Now what we need to do is work our way backwards to try and figure out what these question marks are. So let me get another page going here and a double page display. And we can simplify this a bit. So if we ended up with 98 protons and we started with 2 from our alpha particle and a question mark, that means that our question mark, our unknown element we began with, has to have 98 minus 2, which is 96 protons. Now, if you look at the periodic table again, 96 on the periodic table is curium, symbol Cm. So we know that in order to make californium-245, scientists took a certain isotope of curium and hit it with alpha particles. Now we have to figure out what type of isotope of curium they were using. So now we have to do the same thing with our neutrons. So we have 147 plus 1 is 148 total neutrons after the transmutation. And we started with question mark, whatever our element had, plus 2. So our question mark, our curium, had a total number of 148 minus 2 is 146 neutrons. Now in order to make a complete symbol for this, a complete answer, we need to put together our information for how many protons and how many neutrons we have. So to find our final answer, we have to take our elemental symbol, Cm, and down here is where the atomic number goes, and the atomic number for curium is 96. And then we have to add the number of protons and the number of neutrons. So 146 plus 96 equals 242. So this number up here is 242. So our final answer here is, what was the target isotope that scientists used to make californium-245 by bombarding it with alpha particles? It was curium-242. So when you're solving a problem like this, make sure that you list how many protons and neutrons you had both before and after the transmutation, and you have to balance them. You have to have the same number of protons before and after and the same number of neutrons before and after. Now, some transmutations occur very slowly and with very little radiation, just like Rutherford's transmutation of nitrogen into oxygen. But other transmutations require particles moving at very, very, very high speeds that have a lot of energy. And this is where things like particle accelerators come in. This is a picture of the CERN particle accelerator, which is in Europe, and it is the biggest particle accelerator in the world. And scientists have used this to not only make transuranium elements, they've also used this to figure out the structure of subatomic particles. So scientists have determined that beyond the proton, neutron, and electron, there are even smaller pieces that make up those particles, and those things are called quarks. And there are 6 different types of quarks that we know about right now, and the different combinations of those 6 quarks will make different particles like protons and neutrons. And you can see this is massive. This is one part of the accelerator, and this is a person right here. So this is a giant undertaking, and there are thousands and thousands of scientists who work on this, creating new elements as well as discovering smaller and smaller pieces of basically what make up our universe. So here are the homework questions. Go ahead and work on them and have the answers ready for tomorrow.